but I can hold it. I can hear this thing. I'm just showing. Oh, there we go. Okay, cool.
Right. The second speaker of this session is Kianna Wan from Stanford, who is going to talk about the randomized quantum algorithm for statistical phase estimation.
Hi, everyone. I'm really happy to be here in person and have the opportunity to talk to all of you. This talk will be about.
We can't hear you. Sorry.
Oh, okay. Sorry. Is this better? Is this on? Even higher? Oh, there we go. Is that too loud?
I think it needs to be quite close to your mouth.
Better?
Yeah.
Like that? Good.
Let's try.
Can you hear from the back? Okay, cool. So today I'll be talking about some recent work that I did with my very awesome mentors back when we were at AWS, Berta and Earl Campbell. So we developed a randomized algorithm for phase estimation. But before I launch into what that means, let me give some context. So this work was in part, oh, I can't. Sorry, there we go. This work was in part motivated by the notion of early fault tolerance as a potentially useful regime between NISQ and full fault tolerance. So in NISQ, we usually think of having noisy quantum computers with not too many qubits, so we can only run small circuits. And this typically limits us to heuristic algorithms that evade tight, rigorous analyses, or algorithms for problems that aren't of great practical interest, techniques that aren't scalable, and so on. And at the other extreme, hopefully we'll eventually have a fully corrected fault tolerance computer with lots and lots of well-protected logical qubits. And for these, we already have many scalable algorithms with rigorous asymptotic analyses. But of course, the problem is that we're currently so far from being in this regime. So somewhere in between, we can imagine a scenario where we have enough physical qubits to have a moderate number of logical qubits, so that we can potentially run more complex or interesting algorithms, but still with some limitations to keep in mind. In particular, in such a setting, it might make sense to prioritize reducing circuit depth, in the sense that it might be advantageous to run many smaller circuits instead of a few large circuits, even if the total runtime associated with the many small circuits will be somewhat larger. And perhaps by making such a compromise, we can get some of the best of both worlds, namely algorithms that we can implement on smallish computers while still permitting scalability and rigorous performance guarantees. So with this in mind, so let's look at phase estimation. I took this circuit diagram from Nielsen and Chang, so we can refer to this as standard phase estimation. And looking at the circuit, it's pretty clear that it's not totally suitable for early fault tolerance. We need several logical ancilla, and we need to apply the controlled version of whatever unitary U that we're interested in many times in series. But actually, Kitaev's original formulation of phase estimation uses many smaller circuits, each involving just one ancilla and one of the powers of U. So you run the circuit for a sequence of different integers, k, and for each k value, the measurement outcome on the ancilla will give you a different bit in the binary representation of the phase. So this iterative phase estimation procedure uses somewhat less coherence as standard phase estimation, so it's perhaps a bit friendlier for early fault-tolerant computers. But in this case, the less coherence does come at a price, namely, because we're only learning one bit of the phase at a time. This only really works well if you're given an input state that has large or perfect overlap with an eigenstate of U. Because otherwise, if you have a superposition of eigenstates, then each circuit gives you a different bit, but you can't tell which bit is part of which eigenvalue. In contrast, in standard phase estimation, the circuit just gives you the full binary representation of some eigenvalue. So you can start with a trial state that just has some not too small overlap with an eigenstate you care about, which is typically a more realistic assumption. For instance, let's say we're using phase estimation to estimate the ground state energy of some Hamiltonian. It's typically hard to prepare the ground state with large or perfect overlap, but it's often the case that we can prepare a state that just has some not too small overlap with the ground state. So to work toward an implementation of phase estimation that's both suitable for early fault tolerance computers, but also allows us to use trial states with imperfect overlap, there's a recent approach by Lin and Yu Tong. So for simplicity, they consider the problem of estimating the ground state energy of some Hamiltonian H, which is often a relevant problem in quantum simulation. And as is usual for this problem, we assume that we're given a trial states rho along with some non-zero lower bounds eta on the overlap between rho and the true ground state of H. And then the idea is to consider the cumulative distribution function, or CDF, associated with rho and H. So here, energy is along the x-axis, and the value of the CDF at a given x is equal to the overlap between rho and eigenstates of H that have eigenvalues less than or equal to x. So you can see that the jump discontinuities in the CDF correspond to eigenvalues of H, which means that if we can somehow approximate the CDF, then we can estimate the ground state energy by locating the first jump discontinuity. So to approximate the CDF, Lin and Tong construct a Fourier series, which allows them to write the CDF as the expectation value of a linear combination of time evolution operators, e to the I tjh for different times tj. And then to estimate this right-hand side, they use importance sampling in conjunction with Hadamard testing. So what does this mean? For our purposes, it'll actually be useful to look at importance sampling and Hadamard testing in slightly more generality. So suppose we want to estimate some general linear combination of unitaries, uj. We can do this in the usual importance sampling style by first sampling an index j with probability proportional to the coefficient aj, and then performing a Hadamard test on uj, which gives us an unbiased estimate for the expectation value of uj with respect to rho. And then we repeat this sampling many times and take the average of the results to get our estimate for the full linear combination. Now, the important points to sort of remember from this slide are that the number of samples we need is going to be proportional to a squared, where a is the total weight of the coefficients in our linear combination. And second, you can see that the complexity of these Hadamard test circuits is clearly dominated by the complexity for implementing the controlled UJs. So the expected gates cost per circuit will just be the weighted average of the cost of the controlled UJs. Okay, so going back to Lin and Tong's approach, their Fourier series for the CDF is clearly a special case of this linear combination of unitary setup, where each of the unitaries uj is a different time evolution operator. So that's why their circuits require implementing controlled time evolution. And their algorithm just assumes access to these controlled time evolution operators as black boxes. So arguably, it doesn't go all the way in achieving the mandates of early fault tolerance, because opening these black boxes by synthesizing the controlled time evolution can be quite costly, requiring lots of gates or ancillas. And importantly, this cost would just place a strict lower limit on how large these circuits have to be. So instead of synthesizing the time evolution operators, one of the main ideas behind our algorithm is to randomly compile them. More specifically, we'll decompose each time evolution operator into simpler unitaries that we can then randomly sample from and Hadamard test individually. And I should say right from the beginning that we don't use qdrift or any other existing random compiler to do this. And you can ask me later about why existing approaches don't give us what we want. Sorry, the HDMI isn't working that well.
I think it's the problem with the projector.
This happened yesterday too. I can hold my laptop. Better? Okay, great. Right, we don't use qdrift. Ask me later about why. But let's take a look at our input model. We assume that the Hamiltonian is specified as a linear combination of Pauli operators, which is a pretty common assumption to make and is natural for many problems. And then our phase estimation algorithm works for any such Hamiltonian, and it has some nice advantages over previous approaches. For one, phase estimation algorithms typically have circuit complexities that are at least linear in L, which is the number of terms in the Hamiltonian's Pauli decomposition. In contrast, the quantum complexity of our algorithm is independent of L, and this can be quite useful for practical problems where L can often be large. And the cable is not working. Right, I can try holding again. All right, that seems pretty sure. Okay. Right. Right, so it's sparsity independent, where sparsity is the number of terms in the Hamiltonian. But actually, this sparsity independence feature is quite a generic feature of randomly compiled algorithms. But our algorithm has another feature that previous approaches don't have. And this is that we can trade off between the number of gates per circuit and the total number of circuits, in the sense that to solve the same problem with, for instance, the same error parameters and so on, we can choose to make our circuit shorter by allowing ourselves to run more circuits. And this is very much in line with the motivation of early fault tolerance. But even outside of this early fault tolerance setting, this feature immediately also allows you to parallelize the computation across many, many quantum computers in an extremely straightforward fashion. So now, if this will let me, I'll go over the three main ingredients that go into our algorithm. The first step will still be to approximate the CDF using a Fourier series, but we'll actually construct a different Fourier series than the one used by Lin and Tong, and this is for improving the total runtime. And should I continue? Okay, and then once we have our Fourier series, the second step will be to compile each of the time evolution operators in it into elementary gates. And we show that we can tune the number of gates in each circuit by varying the total number of circuits. And so instead of having a fixed gates count and a fixed number of samples, as with a lot of other approaches, we can get flexible trade-offs. And it turns out that there's actually a large number of parameters that can be tuned to get different sample and gate counts. So our third ingredient will be to show how we can efficiently optimize over all these parameters to find the sort of optimal trade-off curve. Okay, so to briefly look at how we can approximate the CDF using a Fourier series, this part is pretty technical, so I won't dwell on the details. But the basic idea is to write the CDF as a convolution between its corresponding probability density function and the Heaviside step function. And then we replace the Heaviside step function with the Fourier series approximation to it. And I mentioned we construct a different Fourier series from Lin and Tong, and the upshot of this is that it parametrically improves the total runtime of our algorithm in terms of the target accuracy delta. We get these improved error bounds by using a conceptually different approximation, but I'll refer you to the paper for details. So with our Fourier series in hand, the second step is to randomly compile the time evolution operators in it. And our main result for this part is captured by this lemma. So let's say we renormalize our Hamiltonian so that it's a convex combination of Pallies. We can always put the normalization back in later. Then for any real number t and any integer, positive integer r, we can decompose the time evolution operator e to the IHT into a linear combination of unitaries that has the following two properties. So first, the total weight of the coefficients in this decomposition is upper bounded by e to the t squared over r. And second, the non-Clifford's cost of implementing the controlled version of any unitary in this decomposition is going to be that of r many controlled Pauli rotations. So the point of this lemma is to allow for a trade-off between the sample and gate complexities. In particular, the number of samples we need is going to be determined by mu, which is decreasing in r, while the number of gates per circuit is just r. So if we increase r, we can suppress the sample complexity at the cost of increasing the number of gates per sample, or vice versa. Okay, so let's look a little bit more explicitly at how we're actually going to use this lemma to estimate the CDF. Ultimately, we want to write the CDF as the expectation value of some linear combination of unitaries. So we can estimate that using Hadamard testing and importance sampling. So we had our Fourier series for the CDF from step 1. But instead of Hadamard testing the time evolution operators directly, we're going to further decompose them using our LCU lemma. So in our Fourier series, we have these time evolution operators for difference times Tj. So to use this lemma, I'm just going to put the label J onto all of the relevant quantities. In particular, for each difference Tj, I can make a different decomposition for the time evolution operator with a different weight mu j and so on. And then we'll plug these decompositions in to our Fourier series and obtain this double sum. So then to estimate the CDF, I randomly sample unitaries, ukj, from this double sum with probabilities proportional to their coefficients and implement them in a Hadamard test. But what do these unitaries actually look like? This is given by our particular LCU decomposition for the time evolution operators. So let's see how that's constructed. First, we divide the time evolution into r segments, each over a time interval t over r. And then we Taylor expand the operator for each segment. So here I've written the Taylor expansion, the first two terms in the Taylor expansion for e to the IH t over r. And then we pair up consecutive terms in this expansion. So you see, for instance, that and I'll also expand out the Hamiltonian into its Pauli decomposition. So we can see that the first two terms becomes a linear combination of operators of the form identity plus I times some real number times some Pauli operator, which we can recognize as proportional to a Pauli rotation, where the angle depends on t over r. So we see that the first two terms gives rise to a linear combination of Pauli rotations. And similarly, the higher order terms will also give rise to unitaries that each contain one Pauli rotation, but also some sequence of Pauli operators. So the non-Clifford's cost of any unitary in this decomposition is that of a single Pauli rotation. And then to sample the unitary that you actually implement in the Hadamard test, we independently sample r unitaries from this decomposition for a single segment and implement their product. So that's how you end up with circuits that look like this. Here, each Wi is made up of one Pauli rotation, which is represented by a circle, along with some sequence of Pauli operators, which are the squares. So what's the final complexity of our algorithm? It turns out that the sample and gate complexities are given by these formulas, which depends on the Fourier coefficients, the total weights mu j of our decompositions, and the integers rj. So I still haven't fully specified the algorithm in that I haven't told you how you should choose these integers rj. Because as far as the lemma is concerned, we can choose any integer rj when we decompose each e to the itjh. So as a simple example, let's say we set each rj to be equal to 2 tj squared. And then this upper bound on our total weight just becomes a constant, which simplifies our formulas for the complexities. And then after analyzing our Fourier coefficients and so on, we find that the sample complexity is 1 over eta squared up to log factors, where eta was the lower bound on the overlap between our input state and the true ground state. And this makes sense intuitively, because if we look at the approximate CDF, the sort of vertical wiggle you get or that you can tolerate, depends on how big eta is, because we're trying to distinguish the first jump discontinuity. And these vertical wiggles are related to the variance, which we can suppress by taking more samples. And also for this choice of RJs, the Gates complexity is lambda squared over delta squared, where lambda was the total weight of a Hamiltonian Pauli decomposition, and delta is the target additive error. So to compare this to existing approaches, in particular the ones based on qubitization, which are some of the best scaling approaches for quantum chemistry, for instance, the circuits for phase estimation based on qubitization typically have volume that scales as L lambda over delta, where L is the number of terms in our Hamiltonian. Basically, you can get away with square root L gates if you use square root L ancillas. In contrast, the complexity of our algorithm is independent of L at the price of a quadratic dependence on lambda over delta. We also only use one logical ancilla. So in terms of space-time volume, it's looking better when n lambda over delta is smaller than L, which can be the case, for instance, when there's a lot of variation in the coefficients of the Hamiltonian. So then their total weights can be much smaller than the total number of steps. But also remember that these are only the complexities for this one particular choice of RJs, whereas one of the unique features of our algorithm was that we can trade off between gates and samples. So unlike in qubitization and other approaches, we're usually just limited to some fixed gate counts. So this brings us to our third main ingredient, which is how do we actually find the optimal trade-off? Because the RJs we chose in the previous slide were just a heuristic choice to make the analysis simple, but unsurprisingly, it's not going to be the optimal choice. So the first thing we can consider trying to do is to minimize the total expected complexity, which we get from multiplying the number of samples by the number of gates. And I'll also replace each of the mu j's by its known upper bound, e to the cj squared over rj, and call this last expression c tilde. Now let's suppose we want to find a sequence of RJs that minimize C tilde. Because remember, to use our algorithm, we have to explicitly specify which integers RJ that we're going to put in our lemma. So on the face of it, this is a very high dimensional optimization problem because typically there's lots of RJs to optimize over. For instance, we ran some numerics for the Fumoko benchmark, which is a popular benchmark system in quantum chemistry. And to get chemical accuracy for Fumoko, we need millions of Fourier coefficients, which means that there's millions of RJs to optimize over. But it turns out that we can reduce this high dimensional optimization problem into a simple one-dimensional problem. And here's how. So as usual, I'll take the derivatives of C tilde with respect to each of the RJs, and I'll set them all to 0. This ends up giving us this formula for the optimal RJs, which I'll call RJ star. And looking at this, you see that each RJ star still depends on all of the other RJ stars. But the trick is that this big expression at the end here is the same in the formulas for all of the RJ stars. So essentially the idea is that we just have to find the one value for it that makes everything self-consistent. And if we denote this special value by little q star and write everything out precisely, then we end up with this pretty straightforward equation for q star. This is a single variable equation, which we can solve using standard techniques. For instance, we show in the paper that q star is bounded within a small interval. So you can, for instance, use bisection root finding to solve for it in a log number of steps. And then once you've found q star, you just plug it back in to obtain all of the optimal RJ stars. Okay, so that was for finding the one sequence of RJs that minimize the total complexity. But in some settings, like in the early faults tolerance scenario, it might be well motivated to ask the following question. So suppose I want to set an upper limit G on the expected number of gates per circuit. Then what's the sequence of RJs that give me the minimal sample complexity? It turns out that we can solve this more constrained optimization problem using similar techniques. And by reducing it to another one-dimensional problem, and then by solving this problem for various values of G, we can find the optimal trade-off curves. And here's what these curves look like for the Fimoto benchmark, where again, where actually epsilon is another free parameter that we can tune in the algorithm, but I won't get into the details of that. And finally, note that even though we constructed a specific Fourier series for the CDF in order to do phase estimation, our solution to this optimization problem didn't assume any particular values of the FJs and TJs. So our optimization procedure works for any arbitrary Fourier series, or really just any decomposition into time evolution operators. It doesn't necessarily have to be a Fourier series because the TJs can be arbitrary. And likewise, our random compilation scheme of the time evolution operators also, of course, works for any such decomposition. So what I'm getting at is that our second and third ingredients are generally applicable. It's only our first ingredient that's specific to the problem of phase estimation. And many quantum algorithms involve estimating some function of some permission operator. So if you, for instance, construct a Fourier series approximation to whatever function you're interested in, then our second and third ingredients immediately provide a general and completely rigorous framework for estimating expectation values of that function. And it'll give you an algorithm that has the same two distinctive features as our randomized algorithm for phase estimation, namely complexities that are independent of the number of terms in your operator's description and the ability to tune the number of gates against the number of samples. And that's all I had. Thank you.
Thank you for the nice talk. Due to the technical issues, we only have time for one short question, and please take the others offline.
Okay. High pressure. So can you talk more about, maybe you already mentioned it, but I didn't quite understand. How do you do the sampling that you need to do? So you need to sample from these circuits. Did you explain that, or?
Oh, right. How to sample the unitary that you had a more.
Yeah, how do you sample these? Because it seems as though, yeah, you can't just construct the ensemble. It's exponential, right? So.
Right. So you start with this decomposition for the operator for a single time segment. And to sample from this, you can sample according to like the coefficients in this expansion. And then you sample, and on top of that, you sample a Pauli according to its weight in the Hamiltonian. And then you need to implement R of these, the product of R of these. So you can independently sample R unitary.
Oh yeah, okay, fine. Yeah, okay, I should have seen that. Thanks, yeah.
Actually, I was told that we don't have to synchronize with the other sessions, so we can have more questions. One question that I would have is that this improved Fourier series, can you shed some intuition? What is the main idea for the improvement? How do you get it?
Sure. So like I said, our approximation is just conceptually different. Like we start from a different starting point. But my guess for why limit tolerance bounds would be loose is that they ultimately have to bound like the error in some function that oscillates really rapidly around 0 in some regions. And the oscillation clearly, like you should expect large cancellations in that when you take, you have to find the integral over this. But the oscillations aren't periodic, they're only close to periodic. So the only way they can upper bound the interval is to just take the absolute value. So they can't like exploit these cancellations. Whereas in our approximation, we start from a different function and everything works out better.
Thanks. One more question. Okay, cool.
Thanks for the talk. So your algorithm doesn't quite achieve the optimal asymptotic performance of like traditional phase estimation, right? So there's going to be a regime where traditional phase estimation will eventually win out over this technique. I was wondering if you had, like, it's clear that you had done some numerical work to like benchmark the performance of this technique. What's the regime in which you'd expect this technique to be practical?
So we only vary merits for one quantum system, but another quantum system in which we found to have better scaling than cubitization is, for instance, when you're trying to estimate the ground state energy of hydrogen chains with its sense of error. And in that case, because our complexity is quadratic in the inverse error, when you want to tolerate its when you're interested in its sense of error, then you get a better scaling because you can divide by another factor of n.
A factor of L?
Factor of n, where n is the system size.
And it's the system size. I see. So in a situation where your system is enormous, this might continue to perform really well.
Not in the limit when your system is large, in the scenario where you're interested in its sense of error. Or the other scenario in which you might expect this to have better scaling is when there's a lot of variation in the magnitudes of the coefficients of your Hamiltonian. Then there's actually a lot of small terms that you don't really care about. And in this paper, for instance, they truncate these small terms to get a smaller L because their algorithm scales with L. But these truncations are heuristic. They do justify them using numerical simulations. But I guess I should point out that, like, because the analysis of our algorithm is rigorous from start to finish, like we don't use numerical simulation, but it's plausible that when you actually run it in practice, some of the steps that go into some of the many steps that go into bounding the errors and so on will be produced in practice.
Right. Thanks.
Thank you.
Let's thank the speaker once again.